Hello, this is Ashwini. I am a research scholar in the Department of Computer Science and Automation, Indian Institute of Science, Bangalore. I am a TA for this particular course. Today in this session, we will learn artificial neural network implementation. These are the contents of my presentation. First, initially we will be seeing what are the basics that are required for the implementation. Whenever we are designing a neural network, more specifically multi-layer perceptron, how many number of layers are there, how many number of neurons that we are going to place at each layer, and what are the different activation functions that we can put, what are the different optimizers and the loss functions, how to select the loss function, how to select the different optimizers, what will be the impact of optimizers. This is what we are going to see in the first session. And in the second session, we will be seeing the actual implementation of neural network. We will be using a Keras, and then we will see in Google Colab. So let us move on. This is this is one example, and here we see that there is a data set that we have considered, and the data set that we have taken here is an iris data set. So how many number of neurons are there here, how many number of features are there? If you look into this, we have 1, 2, 3 and 4. Because we have 4 features, we have an input layer, we have an output layer. First let us talk about input layer and output layer. Because there are 4 number of features, so therefore we will have 4 neurons at an input layer. Next, at an output layer, see now before we go into output, there is one more basic that we need to understand, whether we are solving a classification problem or whether we are solving a regression problem. Now in this particular example, we are solving a classification problem. Again, under classification we have binary classification and we have an multi-class classification. And if you look into this example, we are dealing with multi-class classification. Now when there is a multi-class classification, count how many number of classes are there. So here this entire is one set of class, this is a second set of class, and we have a third set of class. So here since there are 3 classes, therefore it is a multi-class classification problem. Because there are 3 classes, we are going to place 3 neurons at an output layer. I hope this one point is clear to us. Based on a number of features, if the features are 10, then we will have a 10 number of neurons. Because here the features are 4, we are going to have 4 neurons at an input layer. We will see more specifically going forward. Next comes, we have an hidden layers. Now how many number of hidden layers and how many number of neurons to put at an hidden layer is purely an user's choice. For every data set, the number of hidden layers that you are going to select and number of neurons that we are going to put at an hidden layer will vary. So this is what we have discussed. So because this is 4 features, so we are seeing that there are 4, and then there are in the multi-class classification, therefore there are 3 labels, and hidden layer, as we have seen, there is no restriction. This is one more example, and in this example let us see how many number of features are there. If you count, this is 1, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because we have totally 10 number of neurons at 10 number of features at an input layer, we are going to have 10. And if you look into the label column, we have 0 as one class and 1. So because there are 2 at an output layer, it is a binary classification. Because it is a binary classification, we are going to place only 1 neuron at an output layer. So next, so this is what it is. At an input layer, we could able to see that there are 10, and at an output layer there is only 1 neuron. Why is that there is only 1 neuron? Because at an class label, in the class label we can able to see that there is only 2 classes, whether it is an 0 or 1. Because of this, there is only one neuron. As we have seen in the previous, there is no restriction with respect to number of neurons and the number of layers and the number of neurons that we are going to place at a hidden layer. Now, since it is an hands on, let us look into how we are going to code it. So, if you look into this particular diagram, what is that first we are writing? First we are writing an input, then we have an first hidden layer, we have a second hidden layer and we have an output layer. We are going to place these layers one after the other. Therefore, we are going to build a sequential model. So, we are importing a sequential, and what is that we are using? We are using a Keras to implement, and it is in a sequential model. Therefore, under Keras we are using class called models, and then we are importing sequential. Next. So, we are building a sequential model, and then you see here, because there are 10 number of neurons at an input layer. So, here input underscore dimension we are specifying 10, and this is the first hidden layer that we are writing, because in the hidden layer this is the first hidden layer, and number of neurons that we are going to place in the hidden layer are 32. And why is that word dense? Dense here is one neuron is connected to every other neuron, because it is a fully connected neural network. Therefore, we are writing the word dense. I hope this one line is clear to us. Let us come back to the activation function little later. Next, what is that we are doing? We are including the second hidden layer. We are adding the second hidden layer. When we are writing the second, when we are adding the second hidden layer, to this second hidden layer, nowhere input is being passed. What is passed to the second hidden layer? The output of this hidden layer is passed as an input to this. Therefore, this is the line which is dealing with the second hidden layer. So, in the second hidden layer, how many number of neurons are there? There are 32 neurons at an hidden layer. Okay, that is the reason we are writing 32. And why is that dense? Because it is a fully connected neural network. And what is that last point that we have discussed? At the last layer, what layer that we have here? The last layer here is an output layer. Next, how many number of neurons are there at an output layer? Since it is a binary classification, the number of neurons that we are going to put at an output layer is 1. So, this is what we have discussed so far. Now, the next important point that we will be discussing here is, whenever we talk about this neuron, one single neuron, let us talk about, I am talking about one neuron at an hidden layer. This neuron internally, let us assume there are two functionalities that are going to happen. One here, there is an summation. What is this summation? It is an summation of whatever the connection that is coming to this particular neuron. If you look into this, for this neuron you have a connection coming from this, we have a connection coming from this, and we have a connection coming from this one. And on every connection we will have a weights. We will have a weights associated with every connection. So, at a first inside a neuron we will have a summation operation, which will be the input x1, x2 and so on up to xn, which we have seen in our theory class, and then there is an bias term which has been added. So, we will have xw, then we will have x1 w1 plus x2 w2 and so on up to we will have xn wn, plus there is an bias term b that is being added. This is what is the summation part. Now, let us not bother about this. The next we have something called as an activation function. So, inside a neuron there is an activation function. Rather than saying inside a neuron is the second operation that we are performing here is an activation function. Now, what exactly, what activation functions should be used at each of these layers? So, this is one point that we will be discussing next. So, at an hidden layer, how many neurons are there? There are 32 neurons. For every neuron, we are going to place an activation function. What activation function that we are going to put for an hidden layer? We have a ReLU activation function, rectified linear unit, ReLU activation function. That is the reason you see in this line we have something called as activation function also coming into. So, there are 32 number of neurons, yes, and then for this first hidden layer we are also passing the features. How many features we are passing? We are passing a 10, therefore, input underscore dimension it is 10, and in this neuron there is an activation function also. We are going to place an activation function. What activation function we are using? We are using a ReLU activation. Good. Now, at the second hidden layer, what is happening at the second hidden layer? How many number of neurons are there? There are 32 number of neurons. Here also there is an activation function. What activation function that we are using? Since it is an hidden layer, the activation function that we are using is ReLU. So, I hope it is clear so far. So, at the hidden layer the activation function what we are using is ReLU. Now, the most important is at an output layer what activation function to be used. Now, here also we have a summation part and then there will be an activation function. Now, what kind of problem we are solving? The given data set consists of it is a binary classification problem. Because it is a binary classification problem, we have used a single neuron at an output layer. We have used a single layer, single neuron. Now, what activation function we will be using here? Because it is a binary classification, the activation function that we are going to use is a sigmoid. Sigmoid is an activation function. So, from this what are we, let us quickly summarize what we have discussed so far. The problem definition that we have considered is a binary classification. So, if you can go back, you will see that here there is at an output layer we just have only two classes 0 and 1, therefore, it is an binary classification problem. If it is a binary classification problem, the number of neurons that we are going to place at an output layer is only 1, because at any given point of time the output will be either 0 or 1. We cannot have both the outputs, we will have either 0 or 1. Therefore, there is only one neuron that we are going to place at an output layer. Next, here at an input, what is that value that you will pass for an input? That depends on how many number of features are there in the given data set. So, a given data set, in this particular data set, it is an house price prediction, and I mean house price based on whether a person is buying a house or not. So, here there are 10 number of features. Therefore, at an input we are passing 10. Although there are no 10 neurons, but diagrammatically when you are representing you will be placing 10 neurons. So, we are passing. I hope this is clear to all of us. Now, let us take one more example where we are dealing with the multi-class classification problem. What is multi-class? At an when you take your data set, at the last at the label you will have multiple classes, more than 2 classes. Since it is a popular multi-class classification, that is iris data set, the 3 different classes here are, we have a Sotazo, we have versicolor and we have virginica. So, it is a 3 class problem. Because it is a 3 class, we know that it is a multi-class classification. Okay. So, once again we have to draw. So, and in this particular data set, how many number of features are there? The number of features here are, it is an 4 features. We have petal width and petal length, then we will have sepal length, sepal width and sepal length. So, you will have totally 4 number of features. When there are 4 features, so how is that you are going to draw a neural network? We will have 4 neurons at an input layer, and since it is a multi-class classification problem, how many neurons that you will place at an output layer, that depends on the number of classes. So, since it is an 3 class problem, number of neurons that we are going to place at an output layer is 3. So, at an input layer we are going to place 4, at an output layer we are going to place 3. Why 3? Because it is a multi-class and the number of classes here are 3. There are no restrictions on the number of hidden layers and the number of neurons that we are going to place at a hidden layer. So, when we see the code, look at there is only one hidden layer that we have placed, therefore, you can see there is only one hidden layer that we are writing. How many neurons that we have placed here? The number of neurons that we have placed at an hidden layer is 3. I mean at an hidden layer is 8, and to this hidden layer, let me erase, to this hidden layer, to this there are to this hidden layer there are totally 8 neurons, 4, there are 8 hidden layers. Okay, I mean there are 8 neurons at a hidden layer. Now, to this, what is the input that you are passing? You are passing this input. That means the input features are passed as an input to this hidden layer. Therefore, the number of features here are 4 that is being passed, and we have seen already for the hidden layer the activation function that we have used is ReLU activation function. Okay. Now, at an output layer, how many neurons that we have placed at an output layer? There are 3 neurons that we are placing at an output layer. Why 3? Because it is a multi-class and the number of classes here are 3, Cetazo, versicolor and then virginica. And what is an activation function that we are going to use at an output layer? I think even for the previous we have not discussed. Why is that the sigmoid? I think yeah. So, since it is a binary classification, the activation function that we are going to use is a sigmoid. Now, since it is a multi-class classification, since there are 3 neurons that you have placed, the activation function that we are going to use is a softmax. So, this is what is with respect to classification problem. Now, the next topic that we are going to discuss is a dropout. What exactly is a dropout? So far we have discussed that there will be an input, you will have an hidden layer. Let us take, there are 5 neurons at an hidden layer, and let us take it is an binary classification. So, there is only one neuron at an output. Now, how is that we are establishing a connection? Here when we talk about a fully connected neural network, one neuron will be connected to every other neuron. Second neuron will be connected to every other neuron, and so on and so forth. The third neuron is connected to every other. Similar way, this neuron is connected to this. Now, what is this dropout is all about? Now, we are dealing with the connection. Now, is it compulsory that we should have always the connection from one neuron to every other neuron? The answer is no. We can skip certain connections. Now, what is an advantage of skipping the connection? We can avoid the overfitting problem. Now, how is that you are going to skip the connection? How many connections can be skipped? That is all with respect to a dropout. Now, see, now the dropout can be applied at an hidden layer. That means you can drop some of the connections, some of these connections. You can even drop the input. What is the meaning of dropping an input? Now, for example, if there are 10 features, for a first instance or for a first iteration, I am going to consider only 5 features and I am going to learn. For the second iteration, I am going to consider only 3 features and I am going to learn. In the next iteration, I am going to consider 4 and I am learning. So, at an input layer also you can apply the dropout. So, this is what at a dropout can be applied at an input layer and the dropout can be applied at an hidden layer. So, what we are now first discussing? We are discussing the dropout applied at an input layer. Now, let us go back to the same example, the previous example binary classification where there were 10 number of neurons. Okay. 10 number of features, therefore, we are passing here as a 10. Now, I do not want to consider all the 10 features, I am going to drop a 20% of it. Therefore, we are writing drop and then we are specifying 0.2. So, and dropout, to what you are applying? You are applying to an input. So, that is the reason we are writing a line like this. We are dropping a 20% of the input, which is 10 features. So, out of 10 features 20% is being dropped. Next, at a hidden layer there is no dropout, that means every neuron is connected to and all other neurons at a hidden layer. So, number of neurons that we are going to place is 64, and the activation function, because it is an hidden layer, the activation function what we are using is ReLU. And since it is a binary classification, we see that there is one neuron and the activation function what we have used is a sigmoid. What you need to understand from this particular slide is the dropout. How the dropout, how is that you are how is that you are writing the dropout? There are 10 features, out of that you are dropping the 20% of this 10. So, whenever you are using the dropout function, you need to call its a package, because the Keras has an built-in package called dropout. So, import dropout from Keras. So, this is what is dropout at an input layer. The same dropout can be done even at an hidden layer. So, look at this diagram. At an hidden layer there are certain dropouts. In the previous we have seen at an input layer there were a few dropouts. The connections were made only with the remaining features. Okay. Now, at an hidden layer if we are using a dropout, then how is that we are writing a code? Now, look at this. So, what is the first one? You are writing an hidden layer which has a 60 number of neurons, and because it is an hidden layer, activation is ReLU and the input dimension is 10, because there are 10 number of neuron features. Now, after you have specified the hidden layer, then you are writing the dropout. What is the dropout percentage that we are writing here? We are writing a 20%. Now, is it compulsory that always we need to write a 20%? Answer is no. We can have anywhere up to 50%. So, 10 to 50% is a good dropout percentage. So, once again it is an hyperparameter. You can fine tune it and then see what best suits for the data set that you have considered. Now, we have one more hidden layer, that means we have a second hidden layer. Now, so for second hidden layer also we want to put a dropout. You see how many neurons that we have put at a second hidden layer? 30 neurons. Then what is an activation function? ReLU. So, for a second hidden layer you will not pass an input, correct, that we have seen previously. We are not passing it, that is where you are not having that input underscore dimension here. What is the dropout that we are adding? The dropout that we are adding here is again 20%. Then there is one neuron and a sigmoid activation function. So, a quick summary what we have discussed so far. Now, let us take, if at all if you are solving a binary classification problem, the number of neurons that you are going to place at an output layer is 1, and the activation function that you are going to use is a sigmoid activation function. Next, the second kind of problem that we had seen is a multi-class problem, multi-class classification problem. In multi-class, how many neurons that we are going to place at an output layer, that depends on a number of classes. If number of classes are 3, then there are 3 neurons. If number of classes are n, there will be n number of neurons. Then what is the activation function that we use at an output layer for a multi-class? It is an softmax. So, this is all with respect to an output layer. Then hidden layer, we have seen there is no restriction on number of hidden layers and the number of neurons in the hidden layer. So, there is no restriction. When there is no restriction, so it is purely an user's choice how many neurons you want to place and how many number of layers that you want to place. And what is one point that you need to remember, the activation function that we will be using at an hidden layer is ReLU. Next, for an hidden layer, yes, we can have a dropout. How is that you will be writing a dropout? First write an the line which is specifying all the parameters at an hidden layer, how many neurons, the activation function, and if it is a first hidden layer you will have an input also. Then you pass an dropout. So dropout can be anywhere between 10 to 50% dropout. Yeah, and at a second hidden layer, how many other hidden layers are there? We can add a dropout. Once again, not compulsory that for every layer we should have a dropout. This is an hyperparameter. You can keep experimenting by adding the dropout, and you can leave a dropout and then see how you are having an performance, how the performance is varying. Then the next important concept that we have discussed is the dropout can be added even at an input layer. How is that you will be writing? Wherever we are specifying the input dimension, there only you can write what is the dropout percentage that we want to include. Yeah. So this is all about. Next, the next important thing when you draw a neural network multi-layer perception is we have an quick summary again, because we require an loss function here. There is an hidden layer, there are two hidden layers and there is one output layer. So this is what the neural network. We have seen every connection, every neuron is connected to every other neuron and so on and so forth. Here is where you are going to get the output. At an output layer, at an output neuron is going to produce you the output. Now, once you get the output, this is what is the diagram that you are seeing here. Once whatever the model that is giving you the output, we call that output as y underscore predict. Y predict, the model has predicted it, so we call it as predicted. Then once the model predicts the output, what is that we are going to do? We are going to compare that with the ground truth. So already for every of the sample we will be knowing what is the ground truth. We are going to compare the model prediction with the ground truth. When we compare, what is that we are going to get? If the comparison, if the predicted value and then the ground truth is exactly same, then there is no mistake or there is no loss here. But in reality we never get that. The predicted value when it is compared with the ground truth, there will be a loss. So the next topic that we are going to discuss here is the loss value, the loss function. So what all different loss functions that we have? What problems that we have solved so far? We have solved a binary and we have solved a multi-class. Now, if at all if we are solving a binary classification problem, at the output layer, what is that loss function that we will use? The loss function that we use for a binary classification is binary cross entropy loss. Binary cross entropy loss function is what we are using. Next, if we are dealing with the multi-class classification problem, for example, let us take here we have an example where the label what we have here is A, B and C. Now, whenever we are dealing with a multi-class, whenever we have an labels something like this, what we do? We do certain pre-processing and we convert these labels to something like this. So, what is that we have done? A is converted to 0. And B is replaced with 1 and C is replaced with 2. So, what exactly we have done? We have done something called as label encoding. So, this is called a label encoding, and whenever we do a label encoding, whenever we come across this kind of an situation in your problem statement, then we will be using a sparse categorical cross entropy loss. This is the loss function that we are going to use. Suppose if you have this scenario where rather than representing A with 0, B with 1, C with 2, we are going to change A, we are going to replace A with 1 0 0. Why is that we are replacing A with 1 0 0? How many classes are there? There are 3 classes. What are those classes? The classes are A, B and C. And what is this? It is A. It is A. It is not B, not C. Now, when you take B, it is a B, it is not A, it is not a C. When it is a C, it is a C, it is not B, not A. So, that is how you are going to represent. If you see, C is represented this way, B is represented like this, and A is represented in this way. If you are going to replace the class labels in this particular format, we call it as one hot encoding. If we are using one hot encoding, the loss function that we are going to use is a categorical cross entropy loss. So, for a classification problem, if it is a binary classification, it is binary cross entropy loss. If it is a multi-class classification, again there are two based on how we are going to replace those labels. If the label is converted using one hot encoding, then the loss function that we use is a sparse categorical entropy. If the labels are converted into converted using one hot encoding, then the loss function that we use is a categorical cross entropy loss. Then this is all about a quick summary here. If it is a binary classification, how many neurons that we place here? The number of neurons that we place at an output layer is 1, and what activation function that we are using? The activation function that we use is a sigmoid, and we have seen the loss function is a binary cross entropy loss. If it is a multi-class classification, if you are using an label encoding where you are converting it as 0, 1 or 2, then the number of, it is a multi-class, and number of neurons that you place is depending on number of classes, and the activation function that we use is softmax activation function, and the loss function that we use is a sparse categorical cross entropy. If the label is converted using one hot encoding, then the label will be something like this, and number of neurons at an output layer depends on number of classes. The activation function we use is a softmax, and because we have used one hot encoding, the loss function that we use is a categorical cross entropy. Now, this is something which we have not discussed. Let us see this. Now, whenever we are dealing with a binary classification, now say for example, we have a data set like this. Let us not bother about how many number of features are there. At an for a label column, rather than having the value, usually binary classification, we will see the value, the labels will be in terms of zeros and ones. Instead of label 0 and 1, suppose if the label is -1 and 1. In the place of 0, if you have -1, then we can use at an output layer, at the last output layer, instead of using sigmoid activation, we can even use a tan h activation function. We can use a tan h, and if we are using a tan h, the loss function that you can use is a hinge loss, or we can even use MSE loss. Mean square error. So, how is that we are writing this part of a code? In the hands on you will be seeing the loss here is a categorical cross entropy. That means somebody is using a multi-class classification problem, and probably they have used one hot encoding, therefore, they are writing a loss as categorical. Let us talk about optimizers a little later, and whenever we are dealing a classification problem, the metric that we use to check the performance of the model is accuracy. So, therefore, we have written metric as accuracy. Now, what do you mean by compile? All these parameters we are passing it to a function called compile. Why is that we require a compile is, let us go back to this particular one here. What is that we expect? We pass an input to a neural network, and we expect the model to get the output. Once the model gets the output, you are comparing the predicted one with the ground truth. When you compute the loss, you are seeing that there is a huge amount of loss. Now, to get the output, is it not that we have to execute this? To execute, we use the function called compile. So, for this compile, once you execute, you are going to get the output, and then we are comparing it with the ground truth, and then we are calculating the loss, and then we are also seeing its metric. Therefore, for a compile function, we are passing a loss, we are passing a metric. we are also passing an optimizer. That will be the last point to be that we will be discussing in this session. Let us move further. So far what we have discussed is a classification, but multi-layer perceptron is also used, can also be used to solve regression problems. Now let us talk about what is regression problem and how many number of neurons that we should place when we are solving a regression problem. Now let us assume we have one data set. This is a data set. We have 4 features. We have the first feature, second feature, third feature, fourth feature. Because there are 4 features, we will have 4 our input underscore dimension will be 4. Okay. Next, hidden layers, there is no restriction. We are talking with respect to an output. At an output, what we are solving is a regression problem. When we are solving a regression problem, what will be there at an output? We will have a number. And what number we will have? We will have a real number, or we will have a continuous number. We will have a number something like 0.23, we will have 1.54, we will have an continuous numbers. Okay. Now, so for this, what should be the neural network architecture? How the neural network architecture should be? At any given point of time, regression problem prediction will be a number. For example, if you say what will be tomorrow's temperature, you are going to predict a number. Because you are going to predict a number, just a number, one number, the number of neurons that we are going to place at an output layer will be 1. We will just have only one neuron at an output layer. Okay. So this is fine. Now what is an activation function that we are going to use if you are using an regression problem? So at an there is no problem with respect to hidden layer. It is same exactly as a classification problem. That means there is no restriction on the number of hidden layers, number of neurons at an hidden layer, and the activation function that we use at an hidden layer is ReLU. So this is what is same as your classification, but the at a regression problem, the change is at the output. So since it is a regression problem, you are predicting a number, there is only one neuron that you are going to place at an output layer, and the activation function that we use here is a ReLU activation, a linear activation function. At an output layer, the activation function that we use is linear activation function. So this is what is a regression problem problems if somebody is working on regression. So there is absolutely everything is the same like your classification. There is a change at an output layer. If it is an regression problem, keep one neuron at an output layer, and then the activation function that we will be using is a linear activation function. Okay. Now comes at a compile. When you are writing and when you are compiling your model, what is the loss that we are using? For your classification problem, the different loss functions that we had seen was binary cross entropy, categorical, or sparse. But when we are dealing with a regression problem, when we are dealing with a regression, the loss function that we use is, there are many loss functions, but one of the loss function that could be mean squared error. We can have a mean absolute error. We have many other loss functions such as, we can see there is a mean absolute error, mean squared error, root mean squared error, mean absolute percentage error, or we can have an R2, that is R squared or coefficient of determination. We have these many different loss functions that you can use. So here you can have these in the place of this, you can have any of these, and optimizers, let us put this on hold, and then the metric that we use is, it can be any one of this metric. What is the loss that you are using, and accordingly the metric that we are able to, the metric that you want to calculate. So this is what is the regression problem. Now, the most important concept when it comes to neural network is the optimizers. What is the role of an optimizer? Where is that the optimizer coming into the play here? See, now we have placed the number of neurons, we have placed the hidden layers, and we have an output layer. So far we have discussed at an output layer we are going to get the output. Now once you get the output, you are calculating the loss. So far we have discussed this. Now if the loss is too much, if the loss is very high, which is not at all acceptable one, what is that we need to do? Is it not that our aim is to reduce this loss? How is that we will be reducing the loss here? Now in this entire design, what is that one has assumed? Input is something that you have taken from the data set. So there is nothing that you can do here. Output also you have taken it from your data set only, based on what kind of problem that you have solved, how the labels are, based on that the output. Here if you see, there is an hidden layer and there are connections. Every neuron is connected to every other neuron. So there are connections, and every connection is coming with the weight. So on every connection we will have a weight. So whatever the weights that are assumed initially, those weights are not correct. Probably that is not a correct weights that we have assumed. So what is that we should do? We should come back, because you got an output, you saw that loss is very high. So our aim is to reduce this loss. Now if your aim is to reduce this loss, you have to come back. You have to come back. In this direction you are getting these connections, in this you are getting these connections, and here you are getting these connections, and on every of this connection there are weights. So what is that we have to do? We have to adjust these weights. So during back propagation time we will be adjusting these weights. Who is helping us to adjust? Why is that we should adjust this weight? Ultimately what is the aim? Aim is to reduce this loss. So what is an optimizer? Optimization, optimizer, it is a function which is either used to increase something or it is used to decrease something. Here our aim is to decrease. What is that our aim? To decrease this loss. Therefore we have to use optimizers. So in the coming session we will be seeing in detail about each of these optimizers. We will be stopping here, and in the coming session we will see what are different optimizers are there, and then we will see the hands on using Google Colab. Thank you.